Keeper 7.4, integration by parts. All right, so we have a basic rule for integration by parts, and this rule basically undoes like your product rule. So if you have two things being multiplied, you can't use sub, it's not a trig, it's not an inverse trig. Our next go-to is integration by parts. And so the formula says that we have some integral u dv or uv prime equals uv minus the integral of v du. So you kind of want to memorize this formula. uv minus the integral v du. Now, again, sometimes we have trouble finding our u, and so this is a little rule that we use to help us figure out what the u is, and so we call that Lie8. And so L stands for logs, I is for inverse trig, A is for algebraic, T is for trig, and E is for exponential. So whichever one of these that you have in your problem, you want to go in order. So for example, if I had something that was like an inverse trig and an exponential in my problem, I'm going to let the inverse trig, since I comes before E in Lie8, I'm going to let inverse trig be my U. Or if I had a ln and some algebraic expression, my U is going to be the ln because L comes before algebraic in Lie8. All right, so for our first example, we have the integral of x, e to the x. So x is what we call algebraic because it's like x or x squared or x cubed or x plus 1. Anything like x plus whatever, any kind of like polynomial, that's algebraic. So we have algebraic for our x, and we have an exponential, which is the e to the x. So using my Lie8, I know that I'm going to let u be the algebraic since a comes before e in Lie8. So I'm going to say u is going to be x, and whatever is left over in the problem, so u is x, that means we had e to the x dx left over, that's going to become my dv. So u equals x, dv is e to the x dx. Now I'm going to find du by taking the derivative of u. So du is going to be 1 dx. And then I'm going to find v by integrating dv. So if I integrate e to the x dx, I get v equals e to the x. All right, so now following my formula, I'm going to plug this in. Remember, the formula is uv minus the integral of v du. And so using that formula and plugging my values in, I'm going to have x e to the x minus the integral of e to the x dx. Lastly, I'm going to have to integrate this integral of e to the x. We know the integral of e to the x is e to the x. So I'm going to have x e to the x minus e to the x plus c. Our next example, we have the integral of ln x dx. And so immediately I see that there's only one thing in my problem to start with. It's just ln x. So that by default has to be my u. Not only that, ln is the first piece of our Lie8. It's the first letter. So u would have to be the ln anyway. So I'm going to let u be ln x. And since u is ln x, the only thing that's left for my dv is this dx part over here. So dv is going to be dx. Now when I take the derivative of u to get du, I'm going to get 1 over x, and I'm going to integrate dv to get v, which would be x. So du is 1 over x dx, and v is x. Now plugging into my formula, I have uv minus the integral v du, or x ln x minus the integral of x times 1 over x dx. Simplifying that, I have x ln x minus the integral of 1 dx. And I know the integral of 1 is simply x. So my final answer would be x ln x minus x plus c. I actually encourage you guys to memorize this integral. It comes up a lot. So if you know it, if you just remember the integral of ln x is x ln x minus x, you'll be better off in the future. So again, this would be one that I would memorize. All right, so our next example, we have the integral of x to the 6 times ln x dx. Looking at this problem, I have an algebraic, which is x to the 6, and I have a logarithmic, which is ln x. Using Lie8, L comes before A, so I'm going to use my u to be ln x. And if ln x is u, what's left over in the problem is x to the 6 dx, so that's going to be my dv. Now, taking the derivative of u, I'm going to have 1 over x dx for du, and integrating dv, I'm going to have x to the 7th over 7. Now plugging into my formula, I have x to the 7 over 7 ln x minus x to the 7 over 7 times 1 over x dx. Simplifying that right piece of it, the integral piece, I have x to the 7 over 7 ln x minus 1/7 x to the 6 dx. Now we know the integral of x to the 6 is x to the 7 over 7, so I'm left with x to the 7 over 7 ln x minus 1/7 x to the 7 over 7 plus c. And then cleaning that up, making it look a little bit nicer, and multiplying, I get x to the 7 over 7 ln x minus x to the 7 over 49 plus c. All right, so here's another one. We have x squared, which is algebraic, and we have sine 4x, which is trig. So using our rule for Lie-8, I know algebraic is A, and then trig is T. A comes before T, so U is going to be x squared, and my dV is going to be what's left over of 4x, or sine 4x dx. Taking the derivative of U, I get 2x dx, and then integrating dV, I'm going to get negative cosine 4x over 4. All right, so using my formula, I'm going to get negative x squared cosine 4x over 4 minus the integral of negative 2x cosine 4x over 4 du. Remember, that's the formula, uv minus the integral v du. Cleaning up that integral piece, I'm going to take out the negative 2 over 4. And so I have negative x squared cosine x over 4 plus a half integral x cosine 4x du. Now looking at this integral, I colored it in blue. I notice I have a similar situation as before. I still can't take this integral. I still don't know what the integral is, so I have to do my by parts again. So for just this blue integral, I'm going to let u be x, dv is going to be cosine 4x dx. That means du is going to be dx, and v is going to be sine 4x over 4. So now substituting that in for my blue integral, I'm going to have negative x squared cosine 4x over 4 plus a half, that's from the beginning, times uv minus v du, or x sine 4x over 4 minus the integral of sine 4x over 4 dx. Now integrating that last little piece, I'm going to have the first part, negative x squared cosine 4x over 4 plus 1/2 times x sine 4x over 4. And then the integral of this sine 4x over 4 is 1/16 cosine 4x plus c. Just to make it a little bit more clear and cohesive, I'm going to distribute it in that 1/2 to have negative x squared cosine 4x over 4 plus x sine 4x over 8 plus 1 over 32 cosine 4x plus c. All right, so our next example is the integral of cosine 3x e to the x dx. So looking at this, I have trig and I have exponential, so I'm going to let my trig be my u since it comes before exponential in Lie-8. So u is going to be cosine 3x, and dv is going to be e to the x dx. And so then figuring out du and v, du would be negative 3 sine 3x dx, and v is e to the x. So now plugging into my formula, I have e to the x cosine 3x minus integral negative 3 e to the x sine 3x dx. I'm going to take out that negative 3 out of my integral to have e to the x cosine 3x plus 3 integral e to the x sine 3x. Now looking at this integral, again, it's still an integral that I cannot compute, so I'm going to have to do my formula all over again. So I'm going to let u be sine 3x, dv is going to be e to the x dx, and so du is 3 cosine 3x dx, and v is e to the x. Now plugging that into my formula again, just for the integral part, I'm going to leave everything else alone. I have e to the x cosine 3x plus 3, and then my formula, so parentheses, e to the x sine 3x minus 3, pulled out the 3, e to the x cosine 3x dx. Now, this integral again looks real familiar, but before I even mess with that, I'm going to go ahead and distribute in the 3 that's in front of my parentheses. So I have e to the x 3x plus 3 e to the x sine 3x minus 9 e to the x cosine 3x dx. Now again, this integral of e to the x cosine 3x looks really familiar. As a matter of fact, it is the original integral that we had to do to begin with. And so I noticed that if I do the formula again, I'm just going to keep cycling and repeating and repeating and repeating the same steps over again. So what I want to do is I want to realize that, hey, listen, this expression that I came up with is equal to the original integral. This is what we've been solving for the entire time. So this original integral is equal to everything that we have found or simplified to so far. Well, using algebra, if I add 9 integral e to the x cosine 3x to both sides, I'll be left with 10 integral e to the x cosine 3x dx. So in other words, I took this negative 9 integral e to the 3x or e to the x cosine 3x, and I moved it to the other side by addition to get the 10. Now if I just take that and divide by 10, I get my final answer of e to the x cosine 3x plus 3e to the x sine 3x all over 10. Now, this is what we call a cycling problem. So generally with your cycling problems, you do the formula twice, and then you add whatever you have to the other side or to the original expression, and then divide to get rid of the coefficient. All right, so this next thing I want to show you is just like a quick method for solving these problems. This method, which we call the table method, can be used instead of the formula if your U is algebraic. So if you have an algebraic U, you can use the table method instead of using the formula. Now, don't get me wrong, you can still always use the formula. This method is just a little bit easier and a little bit, not a little bit, it's a lot bit easier and a lot bit faster than using the actual formula. So first thing you want to do when you look at a problem is figure out what your U is. So when I look at this, I see I have an algebraic of x, and I have a trig function of cosine 3x. So I know using Lyate that since algebraic or a becomes before trig of t, I know that my U is going to be algebraic. So once I determine that U is algebraic, I can use my table method. Now what you want to do is you want to set up a table, and your table is going to be set up with U to the left and dv to the right. And so I know since U is algebraic, U is going to be x, and dv by default has to be cosine 3x dx. Now you don't have to put the dx in your table, just say cosine 3x. Now on the U side, generally when we use our formula, we find U and then we find du, so we take the derivative of U. And then when we have dv, we're trying to find v, so we take the integral of dv. And we're going to do that same exact thing in the table. On the U side, so on the left side of the table, we're taking derivatives, whereas on the right side of the table, we're going to integrate. And so I know the derivative of x is 1, and the integral of cosine 3x is sine 3x over 3. And so then I'm going to do that again, and I'm going to do this all the way until my U equals 0. So I know that the very next step, the derivative of 1 is 0, and the integral of sine 3x over 3 is negative cosine 3x over 9. All right, so my U is now to 0. I can't take any more derivatives. That means I can stop my table. So after you get your table, the very next thing that you want to do is alternate your signs. So you always start positive, and then you rotate from positive to negative, however long your table goes. So just keep going positive, negative for the entire table. And again, you always want to start with a positive value for your first sign. Once you alternate signs, the very last thing you want to do is you want to kind of multiply out your diagonals. So this very first x that I have right here is going to be multiplied times the dv diagonal to it. And so x is going to go to the sine 3x over 3, and then this 1 is going to go to the diagonal of that, which would be negative cosine 3x over 9. And I can stop right there because this 0 doesn't have a diagonal to go to. And so if you notice, the only thing that we're not counting is the first dv and the last du. And so once you do that, basically you're going to get your final answer, and you're going to just multiply across. So you're going to have a positive x times sine 3x over 3, and then you're going to have a negative 1 times negative cosine 3x over 9. And so again, that's going to be a positive x times sine 3x over 3 minus 1 times negative cosine 3x over 9 plus c, and of course you would simplify that to make it look a little nicer. So you would simplify that down to x sine 3x over 3 plus cosine 3x over 9 plus c. All right, now that took a little long because I was doing a lot of explaining, but generally that problem would not take more than, I don't know, like 30 seconds to do. All right, so let's try another one. So in this example, we have the integral of x squared e to the x dx. So I know that my u is going to be x squared and my e to the x is going to be my dv, again using Lie-8. So because u is algebraic, I know I can use the table method. So again, u is x squared, dv is e to the x. Remember, on your u side, you're taking derivatives, and on your dv side, you're taking integrals. So the derivative of x squared is 2x, integral of dv is e to the x. Then the derivative of 2x is 2, and the integral of e to the x is e to the x. Then the derivative of 2 is 0, and the integral of e to the x is e to the x. Now remember, after you get your table down to 0, on the u side, you're going to alternate your signs, and then you're going to multiply out your diagonals. And so my final answer would be x squared e to the x minus 2x e to the x plus 2 e to the x plus c. All right, next example, we have x squared plus 2x plus 1 sine of x. Again, my u is going to be algebraic of x squared plus 2x plus 1 because algebraic comes before trig. So my u and my dv are placed into the table, and then from there I'm just taking derivatives. So the derivative of u is 2x plus 2, where the integral of sine x is negative cosine x. And then the derivative of 2x plus 2 is 2, and the integral of negative cosine x is negative sine x. Then the derivative of 2 is 0, and the integral of negative sine x is cosine x. From there, I alternate my signs, calculate my diagonals, and then I write my answer.